Now for the last section of MathXL, starting around problem number 14, we will not be able to rely on a calculator for this, although some calculators can simplify these as we've learned, but I want you to be able to show your work and explain how the result is obtained. So in a problem like this, if we are being asked to find an exact answer using radicals, we definitely don't want a decimal, and we've got to utilize the methods that we've been talking about in class to simplify this. And so what I'd like to remind you of is that the square root of 12, there is no nice number that multiplies by itself to equal 12. But what we can do is we can split this 12 into its prime factors using what we call a factor tree. Now I'm going to look for two numbers that multiply to make 12, and the first thing that came to mind is a 2 and a 6. Now 2 is a prime number. The only thing that multiplies together to make 2 is 1 and 2, the number 1 in itself. So I'm going to circle this. Anytime I find a prime number, I'm going to circle that. 6 is not prime because I can think of some numbers that multiply together to make 6, such as 2 and 3. Well, as we said before, 2 is a prime number, so I'm going to circle that one right away. And then the number 3 is also prime. There's nothing that divides it except for 1 and 3. So I'm going to circle that. What we've done now is we've found the prime factorization of the number 12. And so what that tells me is that the square root of 12 is the same as the square root of 2 times 2 times 3. And you can check, does 2 times 2 times 3 equal 12? And the answer is yes. So these two statements here are equivalent, the square root of 12 and the square root of 2 times 2 times 3. And the reason why we like this prime factorization is because we should recognize that 2 times 2 is 4, and the square root of 4 can be found. Square root of 3, not so much. The square root of 4 is 2, and the square root of 3, well, that can't be simplified, so we're going to bring that down. And as it turns out, by finding a pair of 2's in the original prime factorization, ultimately turned into a single 2 on the outside of our radical symbol. The remaining terms of that prime factorization, or the remaining elements of the prime factorization, does remain on the inside of our radical symbol. And what we've done is we've simplified this square root of 12 component into 2 times the square root of 3. So now, with that side work finished, we can come back to the original problem and simplify. We wanted, I'll just start it right here, 2 times the square root of 12. Well, we just said that the square root of 12 is actually going to be simplified to 2 times the square root of 3. And so this 2 on the outside can multiply by this 2 on the outside. It cannot multiply by the 3 on the interior. That's protected by the radical sign. And so 2 times 2 makes 4. The square root of 3 remains as it is, so we'll go ahead and report this result as 4 times the square root of 3. Now here again, most calculators can't simplify this, but I believe this one can. So what happens when I press 2 times the square root of 12? Well, there it is, 4 times the square root of 3, exactly what we obtained by hand. Let's try that again with number 15. The square root of 28 should be factored using a factor tree, and the first numbers that come to my mind are 2 and 14. 2 is a prime number and 14 is not. Now it doesn't matter what pair of numbers you use at any given time, as long as you reduce this factor tree all the way down as low as it'll go. The next pair that comes to mind is 7 and 2, so I'm going to put 2 inside of that group, or inside of that circle, because it's prime. I should do the same for 7 as well. Since it's prime, there's nothing that multiplies together to make 7. So what that factor tree tells me is that the square root of 28 is really the same as the square root of 2 times 7. And if we employ the shortcut, when there's a pair of numbers on the inside of the radical, it becomes a single copy of that number on the outside of the radical. 7 had no pairs to go with it, so it's going to stay as it is. And I would report the square root of 28 as the square root of as 2 times the square root of 7. And if we're checking our work with a calculator, we could find that the square root of 28 is indeed 2 times the square root of 7. Now in a problem like 16, hopefully you recognize that the square root of 100 is easy to find. That's going to be just the number 10. Square root of 100 is 10. If this was a number that didn't have a nice square root, then we would use the factor tree to simplify. But this one's okay, so we'll move forward. But now we need to think about the square root of x to the 7th power. Well, here again, one of the tricks we learned in the past was that we could just take half of this exponent that's on the inside, since this is a square root. But that's not going to work here because 7 is an odd number, and we can't easily divide that into 2. So let's just remind ourselves that the square root of x to the 7th would be the same as the square root of 7 x's in a row. I think I've got 7 there. And if I use the notion from before that every time that I see a pair of values on the inside of a square root, that turns into a single copy on the outside of the square root, well, here's a pair, here's a pair, here's a pair. So that looks like 3x's will move to the outside of the square root, while 1x remains inside, and 3x's multiplied together could be written as x cubed, and the x remains on the inside of the square root. So when combining this answer with this one, it looks like we end up with 10 times x cubed times the square root of x. And this result has now been simplified. Let's check our work. The square root of 100 times x to the 7th power is 10 times x to the 7th. Well, this calculator let me down, finally. Found a problem that it would not simplify. Now, the square root of x to the 7th has not been simplified. If we try to report this answer in MathXL, they will not accept it. We would want to factor out these factor pairs from the radical symbol, and this solution here is the one that we are after, not what the calculator provided. So in order to keep this last video consistent with the others in around 10 minutes, I'm going to do one more problem, and I'm going to trust that you can use these techniques to simplify the rest of the examples on your own. You can also use the other videos that I've referenced in this class for this week as help as well. Now, what we're dealing with here is a cube root, and we've got the number 256 and y to the 5th. And as we saw just a moment ago, we can't always rely on our calculator. So what I'm going to do is I'm going to create a factor tree out of 256, and I'm going to give myself some room because 256 is quite a large number. So I'm going to create a factor tree here, and the first thing that comes to my mind is 2 and 128. And then this one looks like 2 and 64 to me. 64 is 8 and 8, and by the way, I recognize these as prime, so I could circle them. 8 looks like a 2 and a 4. 4 looks like 2 and 2. And then I come back to this 8 because that wasn't circled, so we weren't at the end of the line there, and I'll do the same thing. 2, 4, and 4 becomes 2 and 2. Your ability to create these factor trees is going to be very helpful in this process, so you definitely want to make sure that you practice this technique. Knowing your multiplication factors helps as well. What it looks like to me is that if we're trying to find the cube root of 256, then that would be the same as the cube root of 1, 2, 3, 4, 5, 6, 7, 8 2's in a row. So I've got 8 2's in a row, and this time instead of looking for pairs of 2, I'm looking for triples of 2. Why am I looking for groups of 3? Well, that was our index for this problem. We need a group of 3 on the interior to become a single copy of that value on the exterior. So this group turns into a single 2 on the outside, and this group turns into a single 2 on the outside. We have the cube root of 2 times 2, only a pair, not a triple, left behind on the inside. So I like 4 times the cube root of 4 as the result for the cube root of 256. Similarly, we have y to the 5th power. So if I continue with my side work over here, y to the 5th power is the same as y times itself 5 times in a row. And if I want the cube root of y to the 5th, then I need the cube root of this expression. And again, we're looking for triples, not pairs. And a triple of y's turns into a single copy of y's on the exterior. We're going to ask for the cube root of y squared on the interior. And now I can combine this expression with this one as our final answer. The 4 and the y from the leading coefficients can be reported at the beginning, and the cube root of 4 and y squared will be reported on the inside of our radical. So as far as a simplified result goes, I would expect to see 4y times the cube root of 4y squared. If you have further questions on this, please be sure to reach out to me through email or as a message through Schoology. Of course, you can also ask for help in class when we see each other next time. Thanks for watching.